Welcome to the second video of Module 3. In this video, we will discuss electrons and their different energy levels. The learning outcomes for this part are: explain the electromagnetic radiation concept, identify the Bohr atom model, identify the different energy levels of electrons, and explain the electron structures in relation to the periodic table. In this lecture, we will explore the electrons in more detail. As we discussed in part 1 of this module, atoms consist of protons, neutrons, and electrons. Chemical reactions happen due to electron movement. Protons and neutrons are never involved in chemical reactions. To understand chemical reactions, we need first to study a special type of energy called electromagnetic radiation. This radiation has a very broad wave that comes with different wavelengths and frequencies, as you can see in the diagram below. Please note that the wavelength and frequency concepts refer to the same thing. The wavelength multiplied by frequency is equal to the speed of light, which is 3 times 10 to the power of 8 meters per second. The symbol for wavelength is the Greek sign lambda. From this equation, we can see that light with a high wavelength has low frequency, which means low energy. For instance, radio waves that transmit radio signals have the highest wavelength and the lowest energy, whereas X-rays have very low wavelength, but very high energy. Light, for example, is a sort of electromagnetic radiation that comes from electron movements, and it is usually classified by its wavelength. From the spectrum diagram, you can see that different wavelengths in meters. We have very short wavelengths, 10 to the minus 12 meters, in the gamma rays, and long wavelengths in the radio waves, approximately 10 kilometers. Humans can only detect a very short range of the spectrum, called visible light, from the color red to the color purple. The range of this visible light has the wavelength of 400 to 700 nanometers. Each color corresponds to a different wavelength or frequency. Red has the highest wavelength, which means a lower frequency and lower energy. The color purple has a shorter wavelength, which means high frequency and high energy. Although we cannot detect any wavelengths outside this range, we have machines to detect and take advantage of these wavelengths. For example, X-rays are widely used in medical diagnostics. One of the many uses of the light produced by electrons is in colorful fireworks. So different atoms produce different colors due to the following two reasons. Atoms emit different electrons with different energy. When electrons carry different energy, they produce different wavelengths or different colors. You can do a simple experiment by sending a white light through a glass prism. You will see the rainbow colors on the other side of the prism. The prism splits the white light that consists of the rainbow colors. You see the change continuously as you pass the white light through the prism. Now what if we change the source of the light? For example, we can use hydrogen gas at very high temperature so that it also emits light. However, you don't see the whole rainbow and you don't see them continuously. What you see is a set of colored lines called a line spectrum. The reason is that the light emitted from the hydrogen gas is related to the electrons from that atom, and those electrons produce certain wavelengths. So different electrons come from different energy levels, and thus they emit light with different wavelengths. Therefore, each element has a unique set of spectrum lines. All this introduction leads us to the Bohr atom model. The model suggests that each electron has different energy levels. The lowest level is called the ground state, and this is where the electrons spend most of their time. If an electron absorbs some energy, it becomes excited and moves to a higher energy level, called an excited state. After a while, it comes back to the ground state, and that's when it emits light at a specific wavelength. The wavelength of the light, which reflects the color, is determined by the difference in energy between the excited and the ground states. From this illustration, you can see that the energy levels are separated and not continuous, so there is nothing in between the ground state and the excited state. And this is why we call the energy level quantized. Let's look at the hydrogen atom again. In the center, we find the nucleus, and the electron is circling around it, which is represented by the blue dots. We cannot locate an electron precisely within an atom, but we can determine the probability of finding a given electron within a region. The area where the electron is circulating is the energy level, or what we call an orbital. In this diagram, you can see the different energy levels available around the nucleus for a hydrogen atom. The N1 is called the ground state, and all other levels are called excited states. When electrons from the different excited levels come back to the ground state, they emit energy. Because the electrons are coming from different energy levels, they emit different energy. Now remember that we can only detect the visible light in our eyes, and this is the reason why we see only 4 lights with the hydrogen gas, as the other emitted energy is not detected by our eyes. Let's study the energy levels of electrons in more detail. There are 4 quantum numbers to describe the energy level, or to describe where the electron is available, and we will discuss each one of them. The first number is called the principal quantum number, or the principal energy level, and we refer to it by the letter N. As you can see, there are 4 energy levels in this diagram. The principal quantum number is also called the shell. So the first shell is N1, then N2, and so on. You can see the energy gap is very big between N1 and N2, and then it gets smaller between N2 and N3, and so on. As the gap between N2 and N1 is the biggest, this means that the electrons emit more energy when they go down from N2, which is the excited state, to N1, the ground state. The second quantum number is called the subshell, and there are different numbers of subshells within each shell. For example, there is only one subshell in the first shell. This subshell is called 1s. In the N2 shell, there are 2 subshells, and they are called 2s and 2p. In N3, there are 3 subshells, and they are called 3s, 3p, and 3d. In N4, there are 4 subshells, 4s, 4p, 4d, and 4f. The third quantum number is the orbital, or the shape of the subshell. Electrons can be in any part of the orbital in any given time. So in other words, we can say that the orbital is where the electron occupies the space. The subshells have different shapes. For example, the shape of 1s is a sphere, and the electrons can be in any part of this sphere at any given time. The p subshell has a more complicated shape with 3 axes, x, y, and z. The p shell has 3 orbitals, namely px, py, and pz. The d subshell has 5 orbitals and a very complicated shape, and we will not cover this in our course. The f subshell has even more orbitals, 7 in fact, and so on. The fourth and final quantum number is the spin. We represent the spin of electrons in 2 directions using opposite arrows, either up or down. Each atomic orbital can hold a maximum of 2 electrons, which must have opposite spins. This rule is called the Pauli exclusion principle. So to describe an electron in the first shell, we say the energy level is N1, the subshell is 1s, the orbital is sphere, and the spin is an arrow either up or down. To represent the electrons from the lowest energy level to the highest energy level, we use an orbital diagram or an electron configuration. There are guidelines to drawing the orbital diagrams and electron configurations. The first rule states that a maximum of 2 electrons can occupy one orbital. We present the electrons by drawing opposite arrows. So when you do the orbital diagram, you could have an empty orbital if there is no electrons left to fill it, or you can have only 1 electron or 2 electrons. You cannot have 3 electrons in one orbital. When you have 2 electrons in one orbital, they have to be in opposite spin. The second rule states that electrons occupy the lowest energy orbitals available and then move to the higher energy levels. So we start with 1s, 2s, 2p, 3s, 3p, 3d, 4s, and so on. Because things become more complicated in the higher energy levels, we have exceptions. The first exception is that 4s actually has a lower energy level than 3d, and they are overlapping. Thus, 4s fills before 3d. More exceptions happen as we move higher in the energy levels, but for the purposes of this course, we don't need to go any further. So the proper order of filling the orbitals is 1s, 2s, 2p, 3s, 3p, 4s, 3d. To do the orbital diagram, we draw a box and fill it with a maximum of 2 arrows. In the electron configuration, we write the orbital and indicate the number of electrons. Let's look at some examples. Hydrogen has 1 electron, so it has an orbital diagram of 1 arrow and an electron configuration of 1s1. Helium has 2 electrons, so the orbital diagram has 2 arrows of opposite spin and an electron configuration of 1s2. Remember that the first energy level can hold a maximum of 2 electrons. An atom with 3 electrons will have its 3rd electron in the second energy level. For example, lithium. Lithium has 3 electrons, so the orbital diagram will be 2 arrows in 1s and 1 arrow in 2s. The electron configuration is 1s2, 2s1. Oxygen has 8 electrons. Please pause the video and try doing the orbital diagram and electron configuration for oxygen. So oxygen has the following orbital diagram. Please note that for the 2p subshell, you have to fill as many orbitals as possible first. So put single electrons first, then start pairing them up until you have used up all the electrons. This is why we have 2 single electrons in 3p. We can abbreviate the electron configuration of an atom by using the closest noble gas and adding the remaining electrons to the corresponding orbitals. For example, sodium has 11 electrons and neon has 10 electrons. So we can write the electron configuration of sodium as Ne3s1. So neon abbreviates the 10 electrons, and we only need to put the 1 extra electron left in 3s. Calcium has 20 electrons, and argon, being the closest noble gas, has 18 electrons. So we can abbreviate calcium as Ar4s2. Remember from Module 2 that the periodic table is organized in a certain way to reflect the elements' properties. So the elements are positioned in the periodic table according to their electron structure. Now let's discuss in more detail the structure of the periodic table. The table is organized to reflect the electron configuration of the atoms, with each row representing an energy level. For example, the first row of the periodic table has two cells which reflect the first energy level, N1. We learned previously that N1 has one subshell only, and it is the 1s orbital. In the first cell, we find hydrogen, and this matches the fact that hydrogen has one electron only. The second cell has helium, which means that helium has two electrons, and the electronic configuration is 1s2. The second row of the periodic table reflects the second energy level, N2. Remember that N2 has two subshells, 2s and 2p. 2s has one orbital, so it can fit a maximum of 2 electrons. 2p has 3 orbitals, so it can fit 6 electrons. For that reason, you can see 2 cells on the left side of the periodic table to represent 2s, and 6 cells on the right side to represent 2p. Likewise, the third row reflects the third energy level, N3. You can see 3s and 3p in that line. Now if you look at the fourth row, you see 4s, then comes 3d and 4p. Remember that 4s has a lower energy level than 3d, and it fills first. The periodic table is designed to reflect this. In this diagram, you can see how the periodic table is organized according to the energy levels. Let's take a look at 2 examples. Lithium has 3 electrons, and it has an electronic configuration of 1s2, 2s1. So lithium is situated in the first cell of the second line, which represents 2s1. Oxygen has 8 electrons, so it has the electronic configuration of 1s2, 2s2, 2p4. You can see that oxygen is located in the fourth cell of the right side boxes, which represent 2p4. As mentioned earlier, we can use the abbreviated electron configuration using the closest noble gas. For example, sodium has the following abbreviated electron configuration, Ne3s1. So sodium has one extra electron on top of the noble gas, and this electron is located in the most outside shell, or the outer shell, and this is what we call a valence electron. Another example is aluminium, which has an abbreviated electron configuration of neon, Ne3s2, 3p1. So aluminium has 3 additional electrons on top of the noble gas, and these electrons are called valence electrons. So in other words, these 2 atoms have 10 electrons similar to the noble gas, and they are very stable. The extra valence electrons on top are the ones that undergo chemical reactions. Elements always try to obtain the stable structure of the closest noble gas using the lowest amount of energy. So most likely, metals lose electrons to have the stable structure of the noble gas. On the other side of the table, we find halogen elements that tend to gain an electron to obtain the noble gas structure, and they become ions with a negative charge. All elements in the same group or the same column share similar properties. That is, they all have the same number of valence electrons. Let's look at some more examples. Sodium has 11 electrons, so when it loses 1 electron, it becomes a positive ion with a structure similar to neon. Chlorine has 17 electrons, and has the abbreviated electron configuration Ne3s2 3p5. So chlorine has 7 valence electrons, and it only needs 1 extra electron to obtain a stable structure similar to argon. As it gains 1 electron, the chlorine becomes an ion with a -1 charge, and the name changes to chloride. So using the periodic table, we can predict how the elements will behave. This prediction especially applies for the elements close to the noble gases. So we can say that groups 1a and 2a from the left side and the groups 6a and 7a from the right are the easiest to predict. For instance, elements from group 1a lose 1 electron and they become positive ions and obtain the noble gas structure. Group 2a elements lose 2 electrons and they become positive 2 ions and obtain the noble gas structure. On the other side, group 6a elements gain 2 electrons and become -2 ions and obtain the noble gas structure. While group 7a elements need 1 electron to gain, and then they obtain the noble gas structure. Elements in group 3a, 4a, and 5a are borderline, and exceptions start to happen, so we cannot accurately predict the charge of these elements. Elements in the D block, the transition metals, are even more complicated, and it is impossible to predict the charge from their position in the periodic table, so you need to learn the charge for those metals. Also, some of the transition metals come with different charges. For example, copper can take either 1 positive charge or 2 positive charges. Iron can take either 2 positive charges or 3 positive charges. So you need to learn those elements and the possible charges that they can take. We will discuss which elements you need to learn in the face-to-face tutorials. This is the end of part 2 recording. Please proceed to the third part of module 3 that will cover naming inorganic compounds.